This is for PLC.
Programmable logic.
Yeah. Well, this is more like a factory. I don't know what's behind it, but the notation looks like a bunch of ladder rungs that it goes down.
Yeah.
But I think behind it there's something else which is never brought to the surface of the PLC.
Well, it used to be relays.
Yeah, it was just made to look like
Back in the day.
And you draw that, and it would be basically how you'd set up the relays to do the control job we're trying to do. And then they built these microprocessor-based controllers to supplant the relays, but they didn't stop using, because they had all these guys that knew how to write these ladder logic diagrams. They didn't change the programming environment, so to speak.
And I'm amazed that what's deep down that I see is very simple. You know, you go through your list of all your inputs, and you find out what they are. Then you go through what you want your program to do with it, and then it goes through all the outputs, and it makes the outputs follow the inputs.
Yeah.
And I mean that could be done in any language at all.
Yeah, you build a big table, and that's all you need.
I think that's how they used to do it when they had, you know, diode grids when they would still roll way back in the old days.
Yeah, but it's one of these things like LabVIEW, where it doesn't really have a concept of time. It just assumes everything is happening all at once.
Right. Well, I thought that was true of the PLCs. And
that's my point.
But it isn't, because what happens is
they're simulating that though.
Well, the thing is, with the PLC, you go down the ladder, and you can do something in the ladder, and you can undo it later on in the ladder. And when it gets to the bottom of the ladder, it's the last known state of anything. So there are PLCs that are immediate like this, and they stay immediate. But the ones I'm looking at, they don't.
Okay.
Alive, Dennis?
We are alive.
Okay. Let's start from the beginning. Okay. Is it okay? I just sit down, or should I stand up?
No, sit down.
Okay.
Whatever you want to do.
Okay. Good.
The cable's not in your way.
Yeah, the cable is, but we can live with it. Okay. Everybody, this is the Silicon Valley Fourth Interest Group, and this morning, the morning session used to be called the Fourth Modification Laboratory. Yeah, that's because all fourth programmer thinks that he has the best fourth. So this is a time for everybody to come up and tell people why his fourth is better than anybody else. So that's so you need to modify fourth my way. But this morning, what I'll be talking is mostly C. And so I thought this is a C modification laboratory. Although I'm not really go down to the bottom of the C compiler, but I think there's lots of shortcomings in C that we can fix in order to achieve what I might want to do, is to compile a complete fourth with C. Okay. So let me see. So I'll talk about the latest ESP32 fourth. That's version 6.1 and 6.2. And I'll talk a little bit about the Python microassembler. That was the first experiment I did, try to build a microassembler to assemble fourth, to construct the fourth dictionary for the C compiler to run with all the C-coded fourth virtual machine. Okay. So then I move the macro assembler to Arduino C, and one of the problems in a macro assembler is how do you jump the labels. So you use a lot of labels to indicate where you want to jump. But labels are problem if you are forward referencing. So if you define, you want to jump to a label which was not defined yet, you got trouble. Okay, so I spent lots of time trying to fix the labels. And then finally I feel, well, because if you use labels, the compiler or the assembler has to run twice. The first pass, you get all the variables, the location of all the variables, all the target addresses. And in the second pass, you can assemble the correct target addresses. So I was thinking, oh, you know, I can do the second passing manually, but I will not be, I should not expect that users of the system would do the second pass manually. So to try to automate all the compiling, and I was reminded, you know, Chuck has solved the problem long time ago, you know, one pass compiler. The fourth has the one pass compiler there. So why not do it that way? So, you know, so in the version 6.1, I use labels and to do the assembly. And in the 6.2, I just create a lot more macros so that all the structures can be assembled in one pass without labels. Okay, so that's basically what I try to do. So, you know, in fourth, we are talking about meta compilers. So meta compiler is like this metamorphosis. You have little worm grow up and finally a beautiful, it turns out to a beautiful fly. So this is the meta compiler, where we want to construct a beautiful thing from an ordinary thing. So ESP 32/4, basically I try to emulate a 32-bit microprocessor, which the EP32, which was all the design was from Chuck's MUP21. Okay, so the fourth virtual machine can be written in C. There's no problem. All the primitive functions can be coded in assembly or can be coded in C. But the problem is the dictionary. So dictionary has all the records of a full system, and it need to the virtual machine needs to have that big structure so that it can actually execute code placed inside the dictionary. So when I first developed the C for fourth, or I call CE fourth, I was not able to construct the dictionary in C. So I thought, well, I just use fourth, construct the dictionary, and then import the entire dictionary into the C code. That's a big array. And so I avoid the tasks of actually constructing the dictionary in C. But it's becoming quite uncomfortable for me because, you know, when I send out people this fourth in C, I have to also send them the meta compiler in fourth. And I have to explain everything in this meta compiler and the C code that's meta compiled into this dictionary. It's becoming a very tedious, and it's. I think people would have a hard time grasp what I'm trying to achieve. So I need to have the C compiler to construct the C, construct the dictionary in place, and then, you know, in one file I just give out to people, and Well, everything's there. You don't have to learn anything. You don't have to learn forth to use it. Of course, when you have it, when you boot it up, it is forth, and you have to learn how to use that. But the compiling process does not need any prior knowledge of forth. Okay. So here is some highlights of the ESP forth 6.2. So I'm using 71 primitive bytecode, and many of them are not used because they are not needed. But I have allocated that many bytecode. So I have a finite state machine which would execute bytecode or bytecode sequences in memory. And I have kernel words which contain list of bytecode. So the kernel words has just a list of bytecodes. The finite state machine can execute them one by one. The colon word contains address lists. Okay, so they are just a bunch of tokens, and tokens are just addresses which the the finite machine knows where to jump to, and then process the list. But one of very nice thing I'm extremely proud of was the stacks. So I used 256 level circular stack. Okay, and each level is 4 byte or 32-bit word. So you have 256 of elements in a circular buffer, and the circular buffer is managed by one byte pointer. So this byte has only 256 locations to point to. So this stack, both of the return stack and the data stack, would never overflow or underflow. So it's always usable. And of course, if you push wrong things, if you pop too many things off it, the program would not work, but the system will never crash. Okay. And I don't have to check the stack anymore. I don't even have to know where the top of stack is. All I have to do is display the top 4 elements on the stack, on the data stack, and you figure whether your code works properly or not. Generally, you put a -1. All the stack are initialized to be 0. You put a -1 as your top, and you do your work, and come back and see if that -1 is still at the top. Okay, if it's not, well. So, and another very interesting that I realized a couple months ago was that forth is actually eval. Okay, eval. So that's a fourth word, which is generally deep down in the nested inside the interpreter. Okay, but eval is the essence of forth. Okay, so if you realize that forth is just this small routine eval, then forth can be treated as a subroutine in a bigger operating system. So you just you set up everything. So eval expect a string, a list of words placed in memory somewhere. So if you give eval the starting point of this string and the length of the string, and the eval would go interpret the words in this list. And this is the key in the ESP32 or the later versions. Then we can make forth a subroutine, and the operating system, when it is ready, when it had this string ready, so it will give eval the address and the length of the string, and eval will do the processing. And when eval finishes this string, it will return to the operating system. So this, I think, Brad used it to incorporate this mechanism into his browser. very successfully. So I think we are very, very pleased with that. And in the sense, I think fourth is always stand alone. We always want to grab everything and control everything ourselves. But this force-centric view may not be very useful if we have to deal with the complication of our environment.
So if I understand you correctly, we could actually use this in C programs and call like just have one line that sets up the string that we're going to pass.
Right.
The second line calls it, and then fourth is called and returns back to.
Yeah, sure. Yeah, no problem. And this is even very useful in the disk interface. So we have a file stored in the flash memory, and we have tools to pull that file into the memory space that we can process. So what I did was pull the entire file into the top half of the memory space, and then I give the starting point, and I know how many bytes I've read from the file, and give these two parameters to eval, and the eval just compiled the entire file. So that was very, very powerful. And so then the one-pass macro assembler. So I'm writing a macro assembler in C, and that would understand the dictionary structure and compile all the records correctly in the dictionary. Finally, once the dictionary is built, the finite state machine was evoked and everything runs. Okay, so I think the last one is a turnkey application. We developed this full system anticipating it will be using many different embedded applications like a robot. Okay, so we developed the core of the fourth and put them into the dictionary, but the application will be placed in the fourth code will be placed in memory, in the flash memory. And when the fourth boots up, the first thing it does is to look at that file and copy the contents of file into memory and compile it, and then bring up the application.
So I did incorporate an SD card, so we can have fourth source code on the SD card. Right?
Yeah. We just need to know how to put things into the SD card and how to read the file out.
Are you going to implement the blocks?
No. The Arduino has the SPIFFS. It's a small file system. So it can it has utility which can move a text file into the flash memory as a file in a very simple directory.
So it moves it from the SD card into flash or into RAM?
I think it's best to place in flash because we got 4 megabytes of flash. So you really don't need an extra SD card. Yeah, if you can write the file directly into the flash, that's what I did here. And then you don't need an extra memory unless you have a huge amount of data that you have to store and you have to access in the runtime.
Yeah, I'd like to see your
Yeah. Okay. Yeah. Sure. Yeah. Well. So that was when just before the Maker Faire, my wife had a stroke.
How's she doing?
She's fine. I was able to left her at home and tell her, "Don't walk outside, okay?" So she was in the emergency room for a couple of days, and finally the Peninsula Hospital discharged her into a rehab center in San Francisco. So I accompanied her into the rehab center, and she said, "Well, you probably should stay here. I said, yeah, sure, why not? So I just camped in her room, set up camp in her room, and stay with her for 3 weeks. And I didn't have send her to the rehab center. I didn't bring my computer. And I said, oh, well, so I just left the big computer home and said, okay, I stay with her. Finally, she got me by 100% attention for 3 weeks. Yeah, so it's like a honeymoon, okay? And so just stay with her, have nothing else to do but watching her. I was thinking, yeah, well, we can do better in the sense that the fourth dictionary, the problem I had was that I don't know C enough to build that dictionary structure. Okay, and the big John, he wrote fourth in C, and I look at it, he's just try pretty much manually fill in the data to construct that dictionary, and it's not not very pleasing. It's very complicated. So I thought, well, the dictionary, I don't know C enough to construct the dictionary. And the problem with the dictionary is that the name field is variable length, and the parameter field is variable length. So you have to there's no easy way to represent variable length records in C. I think if you have fixed length record, C you can declare array and you can assign lots of different. The length is different. Then, well, you have to use pointers. Yeah. So but I think the problem is to construct that dictionary, and in C, I can write out data out to a file quite freely. Okay, 1 byte at a time. So however you want to arrange things, you just write it out to a file. So that kind of capability is what I need. I'm writing out a file in C in fourth anyway. So why not write out the file from C? But C, I don't have a good C system to experiment with. And Python was the one that I had ready access. So I thought, well, let me try to build the dictionary in Python. And first, I thought I would just write our data in a file, because I know how to write bytes and words out into file. But then I found that well, you declare a big array and just fill in data into the array. It's much easier. And you can, in Python, you can look at the array. You can examine anything you do quite easily. In C, you have to compile things and then examine the file. It's much more difficult. So I used Python to first write things out to file, and I found that if I can just easily write things into a big array like a file, but I can examine the array much more easily. So Python is it's a better platform to try out these new ideas. And so I try to construct a fourth in Python. And after, I think, after 2 weeks, my daughter came to visit, and then she asked, what do you want to bring to the hospital? I said, oh, why don't you bring my computer? So in the final week, I got a computer and tried to run these things in Python. and actually construct the entire fourth dictionary in Python. And so that's with that success, I was quite confident that I can do it in C. So I'll move everything over into Arduino. So the essence is that I need to write a macro assembler to put things into the big array. And the things I want to put in are basically bytes and words. Okay, so if I have the basic instructions to place bytes or words, consecutive bytes and consecutive words into this array, and then I can use it to construct any data structure in a big array. So Python is Python syntax is very close to C. So anything I do in Python, I probably can move the source code to C with very minimum changes. And so the C micro, of course, I want to write everything on Arduino because that's where all the code for the ESP32 will eventually go. And I think that C compiler is just as good as any other C compiler, but much more convenient to use. So Python, okay. So I wrote these macros. Write an image, write an integer, and that's comma. That's what we have in fourth, comma. And if I write one byte, consecutive byte, that's C comma. So if I have these two routine, basically I have an assembler, okay, and it's just how you want to arrange things. So I have the code and colon and label. So the code would assemble a kernel word. You give it a name, and then you give it a list of a bytecode, and we just construct the header, and then stuff all the bytes into the code field. So that's the kernel words or the primitive words. And in colon, you do the same thing with the head, but in colon you first write a do list bytecode to start the list, and then you follow with a number of labels. Okay, so all the labels, all the code, colon, and the label, they will return a value, and this value for the colon and code, it returns CFA. Okay, so when the code routine is executed, it returns a value, and this value are assigned to an integer, to a variable, and this variable will be invoked when I compile the token list in a colon definition. Okay, so the essence is that the code and colon returns CFA, and this CFA will be they are assigned, they are defined as variables. The name of these variables are invoked in the token list of a colon definition, and the colon would compile that list. And the label works pretty much like colon, but it doesn't have a header. So it does have it just have a code field address, okay, and that address is returned to the label. So the label knows where that list of words starts, okay, and this is the location when you want to do a branch, you branch to. So you have compile a branch instruction and invoke that address, and you will compile the branch and with the correct address. But that address has to be correct. Okay, if it is a forward reference, it's initialized to a 0, so it's not right. But when you first pass through, all the addresses are filled into the labels. So after one pass, if you list out all the labels, you got the right address. You just copy that list of address into the initial table, and then you recompile it. Everything will be resolved perfectly. Okay, so with these three macros, I was able to construct the entire fourth dictionary correctly. And when I'm compiling, I was compare the I generate with the array generated by fourth byte for make sure that everything is compiled. I can reproduce the entire fourth dictionary as I generate in fourth. There's no reason why this thing would not work, and it did work. Okay, so I think what I did with the Python was just make sure that I have everything lined up correctly to generate a correct fourth dictionary. But since I couldn't exercise things in Python, not much done with the Python experiment, except that I have a file which has all the macros there and all the code that's converted into this particular format. What I want to do is show you the Python code. So this is the Python file. Okay, so the Python file, it just first defines the link. That's a link. That's CFA, and the fourth array. Okay, and then these are all the bytecode that the virtual fourth engine expects. So with all this bytecode, I can assemble kernel words or the primitive words. And here are these macros. The macros just built at the header. You need to first put up the link field, and then put up the name field. That's the head. And once you have the header built, and for the primitive words, you just attach a list of bytecode. And for the colon word, you put a 6, and that's a do list bytecode, and then follow with a whole bunch of high-level code. Okay, so you can see here, these are the kernel words. Okay, here these are all user variables. So you have a HD, span, and the base, and it's just compiled like a constant with a value with an address at the beginning of the dictionary. So the constants are compiled with this bytecode, and you get more complicated things, and then, but all this I try to implement as many primitive words. If the words doesn't involve any logic, it can be coded very easily in C. Okay, and so if they don't have any logic in it, it's just going to be straight bytecode sequences. And anything which has logic in it must be coded in a high level. So this is a whole bunch, about 71, more than 71, because 71 primitives. It produces lots of other things like blank is constant 32. All these things can be done at the lower level. And multiply, divide, the m/mod, all this multiply, divide, all this code can be coded quite easily in C. And this is the high-level code, the colon definitions. Colon definitions, you use a colon, and the definition will return a value which was assigned to a label called fill. Okay, so you do swap 2R swap branch. So you have a branch to fill 2. Okay, you have to branch over here. So these labels allow you to do the branching. Okay, so all these labels, if it is a forward referencing, when this whole thing started, all these labels are initialized to be 0. And then when a label or when a word is compiled, the label is replaced with the actual CFA. Okay. So once you have if the table is initialized correctly, this branch will assemble a correct address to do a branch to here. Okay. And so this is and this each of this column would take the name, the length of the name, and followed by a whole bunch of a variable length of parameters, which are compiled as tokens in a list. Okay, and Python was very nice. It can take care of variable length parameter lists. It's very easy to code it that way. But C would not. Okay. But that's so the this way I was to compile the entire dictionary and verified the entire dictionary byte for byte. And of course, this I can. There's no reason why I cannot just automatically decide the length of the string. So this is mostly not necessary, but there are immediate word and compile only words, which has lexicon bits in the name in the length. And so to take care of that, I need to just specify the length explicitly, because there are for the immediate words, the bit 7 will be set, and that has to be specified explicitly in the length byte. Okay, so that's the Python. So I have I define a bunch of macros which expand the comma and C comma function in the meta compiler in forth, and based on that, I can build all the variable length fields required in the full dictionary. Okay. Okay, so the final task is to move this macro assembler to C. Okay. So I've always complained that C is not very well equipped to compile an interactive OS like forth with variable length name fields and the code field. But this shortcoming can be overcome if I write a bunch of macros. The macros based on the C comma and comma can force C to construct the necessary fields I need in forth, even variable length bytes or variable length. So, and the first effort in version 6.1 was coding these macros. So the primitive words and the colon words basically share the same header structure. So I use the header macro to construct the link field and name field. And the code field would add the variable length bytecode into the code field. And colon would add a 6 first for do list, and then compile a list of tokens, which are just address, CFAs of other words. And the label basically took care of branching. So I basically assemble sublists, label, assemble sublists with address, okay, so that you can jump into any segment of code inside that colon definition. Okay, and the way to do it right is that you have to view the data array differently because we have a byte data and we have word data in the system. It's kind of hard to mix byte and word in the assembling process. So what in the virtual force machine, I have already realized the problem with it, because the bytecode are bytes and high-level token words. So I have to deal with these two different data. And the way I did it was that declare a big array, big integer array, and define an alias of this array as a byte array. So, so the data array are basically words. When you refer to the data array, you are storing words in it. And when you're referring the C data array, they are the same array, but you use byte pointer for this array. So here you can assemble consecutive integers into the dictionary. So IP is increment by 1, but that's the word pointer. So it points to 32-bit words. And when you want to store byte, you use C data, P++ equal to C. P is a byte pointer. And you have to sync IP and P always. If IP is changed, if P is changed, you have to sync them so that they move along, and they always pointed to the same new location that you want to put the data in. So by syncing these two pointers, I can switch between assembling bytes or assembling words. But the macro assembler would have to be able to take care of that. So the header code is basically, I have a thread. This is the link. And when compile the header, I first compile the thread, which points to the previous name field, the name field of the previous word. Okay, once you have that, then I will resync this P and IP, And of course, I have to renew the thread so that the next word can compile its link field correctly. And once that this is compiled correctly, then I'm starting to compile the names byte by byte. So this name field is variable length. We have to force it to end at the word boundary. Okay, and this code would keep on compiling, adding zeros to the end until it hits the byte boundary, word boundary. So this is how you construct the header, which has a link field and a name field. Okay. So this is the code. The code which the IP, when you finish a header, IP is pointing at the code field. Okay. So this code field, I have to save it. This location, I have to save it. And at the end, I'll return it. So this code will return the CFA of the primitive word. And once you have that, this is a VA list, a VA start, a VA end. These are the C doesn't have a good mechanism to compile variable list, variable parameter list, but some smart guy extended so that you have a VA library to give you that capability. So you have to start a list, and then and this one is to how you access the consecutive parameters in the, you attach to the list. So here you have get the next argument. This argument will be integer, okay, and it will be added to the list as a byte, okay. So this is the way to compile the bytecode list. And then
Dr. Ting, if you wanted to avoid having to put the count, what you can also do is if you can reserve a special value at the end, you can just loop until you see
okay.
an end.
I see. Oh, well, but yeah, that's
how
right.
long your words are.
That's right. Yeah, but I think I was looking up in Googling how can I do variable list, and this seems to be the first one which came back, and it looks ugly. You know, in Python, looks very natural because it has this capability already. Yeah. So here are the bytecode that I defined. And these are bytecode. These are the primitives are defined in C. So I cannot use the name again, and I have to do have to assign a different name for the assembler to assemble them. Okay. So these are the bytecode, and once I have the bytecode, I can construct all the low-level kernel words like this. Okay, all these kernel words, you give it the header, compile the header, and then attach a list of bytecode into the code field. Okay, so this is the way to construct all the using this code macro to construct all the primitive words. And the colon, very similar. It's just that the first word is a do list, and this is still this is the bytecode. Okay, so you have to compile that bytecode as the first byte in this word. Okay, the rest of them are just zero. So it's in essence, I need this bytecode 6 to interpret the list. And once you have that word in the code field, and then you construct the parameter field with with all these parameters. These parameters are basically CFAs, and you just read the CFA into J, and then compile J consecutively in the dictionary. And because this thing is always byte, all words, so there's no every word ends at the per word boundary. You don't have to worry about it. And if and at the end you return the CFA. Okay, so this is the how I cheat C to do what I want. Yeah. Yeah. So that's the C modification laboratory, right? And the label is that you have to this forward referencing problem with referencing. So label is to name, give a location of a particular word, but you can attach or a number of tokens after that, because what we care is the location of this label. And of course, after that, you can assemble as many tokens after that when the code needs. And it also return the address so that it has a correct address. And because all these integers are declared as integers, so they have the proper address in that variable. And this variable, when the macro assembler encounters them in the colon word, it would put the proper address into the dictionary. Okay, there's lots of labels that many of them are backward address. So the address is no problem, but those which are forward, you have to reinitialize them properly in the second pass. So labels are all initialized to 0, and when it encounters code, encounters the label name, it will backfill the proper address into these variables, and so they can be used correctly in compiling the colon list. So, so the first pass, no problem, but the second pass you have to do it. I haven't found a good way to do it automatically. Okay, so I was able to do it manually, and just a proof of concept that I can do it. So here are a bunch of colon words. You have the header and the key. You have query key and Q branch key +4. So this one branches to here. This is a begin until loop, and once you get out of it, you just exit. Okay. So here these are the you do the header, and then do the colon, and these thing, all the colon returns a value which will take up by a label or variable, and there's a WITHI. Later on, if it encounters in a list, it compiles the this CFA correctly. So this looks lots of work.
So you were reading from key before you were setting key?
Yeah.
This will read from key before that actually happens.
That doesn't seem to have a problem.
Oh.
Okay. Because I think I think colon returns a value and put it in there before it does anything else. And so here the key has already has already correct address there. So +4 is okay. I didn't have problem with it, okay? So I didn't think too much. Okay, this is one of the more complicated word, fourth, which is to find you have a string and you want to compare the string with all the names in the dictionary and try to find if there's a match. Okay, so header there, no problem, and then the first segment is defined with a colon, no problem, and next these are many labels, because here there's a Q branch to F4, so it has to jump to here. Okay, and then there's a Q branch find 2, which then has to jump to here, and the Q branch find 4, and at the end it would have a Q branch to find 1. So this is a big loop looping through the entire dictionary. And here, code-wise, this is the correct way to express the word, but it's just that when you are referring find 4 was not correct at that point. It was at 0. So the first pass through, it compiles a 0 there incorrectly. But once I compiled everything and all these labels has the proper values, I dump out all the values of labels and then backfill them into the list of labels. And so that would solve the forward referencing problem.
We're having traffic. Just talk
loud. Okay, yeah, sure, okay. All right. So these are labels that need to be reinitialized. So you can see after the first pass, I got all the right numbers, and I just put them back in with the word editor, the editor in Word to fill everything. I think I even use Excel. So I have the list of all the labels, and then when I get the value, get all the correct value, I just copy them out and then put in the Excel and use the Excel to align the fields, and then use Word to put in the square, the equal sign in, and int in front. So there's a lot of manual labor involved in. So this is the symbol table. So while assembling, fourth macro assembler spills names and code of all fourth words to the serial monitor. So in the code, I have a print statement. So when assembling anything, I'll print this name, I'll print all the code, all the bytecode that assembled, and all the tokens it assembled. And I'm not sure of everything. When I'm compiling the header, I have the current link field address. I just print out everything between the last name field to the current name field. So I got everything, all the data there to make sure that I can see everything. So and in one instance, if I just want the labels, I would suppress all the print statement except the labels. The label. I just printed one list of the new labels, so that I can move them back into do the second pass of assembly. So I was spend lots of time comparing things byte for byte, just to make sure that things are correct. And once I got tired of doing this, looking at things one byte individually, I said, oh, I just write that code to the Intel hex dump with the checksum, right? So I can look up, I can compare the checksum. If I find anything wrong, the checksum would tell me, yeah, something's wrong in this line, and I can look up. So there's a little piece of code which does the hex dump. And to do the same thing, I changed my meta compiler in Sharp to do exactly the same Intel hex dump. So I have two dump files, and I can compare the checksums to find out if I've compiled everything correctly. So this is the Intel dump. So I have a checksum which basically print out one line of 32 bytes, and with a checksum in the back. So this is kind of nice. And with these tools, I was able to assure myself that I can generate the dictionary exactly as I have it in the ROM 54. That was the ESP32 Force version 5.4. This version was basically the serial terminal interface. I think the web facing is much more complicated, so I'll leave it to Brad. Okay, so once that I can verify that I generate the dictionary exactly as I've generated in ROM 54.h. And actually, once that's verified, the code just worked. Okay, there's no reason not to work because I have exactly the same two dictionary. I verify every byte, right?
No reason why it didn't work.
So this is the point of 6.1, version 6.1. Okay, so this is I have a file which generates that forth completely in C. Okay. So I have a complete E4 system produced file. And labeling is still a complicated process. Some will have to figure out how to implement single pass C compiler, right? Well, all right. So I think continue on this. I think, well, a Forth-like single pass macro assembler can be coded in C. Instead of labels, instead of this label macro, I need many, many more macros to deal with the control structures in Forth, the way Forth does it. Okay, so I need if, else, then, for, next, begin, until, again, while, repeat, f. All this immediate words in Forth has to be coded as macros, so that they can take care of the assembly, and especially the target address or the forward all the referencing. Because
AFT, not familiar with that. AFT? Not familiar
oh,
with
AFT is used in the for and next. So to skip the first time, you skip at the first time, and then later on because the 5 for next would do 6 times, right? So with the after and then you can skip the first time. So 5, 4, after, then, next would only do 5. Hmm? Yeah. Well, Bill Minch did it. It's very, very, very beautiful, very nice. And so this is the 6.4.2. High-level false words cannot be coded similar to native false code. All words can be assembled in a single pass without labels. Okay, and to accomplish that, you need a stack to stack up the addresses so you can refer it back. Okay. To resolve the forward referencing. Okay. So, but I do have 2 stacks already in the code. Right? Why not use them? But the data stack is more complicated because the top is cached in a register. So the return stack is clean. So I'm just using the return stack to do the compilation, stack. Okay. So whenever you have something that needs to be resolved, you push that address on the return stack, and then later the word will pick up the address, and when it knows the address to backfill, it would get the address and put it back in the pointer that's been saved on the return stack. Okay, so. Again, yes.
Care to estimate how much more you have?
I think we are almost at the end. Okay.
So less than 10 minutes?
Yeah, less than 10 minutes.
If you felt you wanted to go on for a
while
longer, we could continue after lunch.
No. I think I'm almost at the end.
10 minutes, deal.
Yeah. So here, the colon word, instead of the labels, I use begin until. Okay, so it is key doesn't compile anything at this point. So it the begin comes immediate. So you have the begin, query key, and until, then next. So this begin give the address here, and until will pick up that address and compile the proper QBrain instruction for that jump. So the in here 2 character has an if else then. Okay, so it compiles everything there until it comes to the if. So just like for, you do the if, and it compiles the true clause, and end will terminate it properly. Yeah. So well, fourth is beautiful, right? And this is the find that I show you with 6 labels, right? And instead of labels, I just laid it down as just copy the fourth code and put and these are all in the fourth code. The begin, if, else, then, while, repeat. Okay, so this if, else, then is nested in this if, else, then. Okay, and they all do properly, and it's just the fourth code, but I have to write it in the according to the syntax required by the macro assembler. And because the C normally does not call a variable length routine parameters, and when with that the mechanism, the VA list mechanism, you have to specify how many parameters in the list. Okay, and in Python you don't have to.
You have to manually count them and put them.
No, yes. I have to do that. But sometimes I got the compiled run. Suddenly everything's moved ahead. It's because I forgot to put the correct parameter. So it assembles lots of garbage, and
you added a CFA and then
yeah.
No,
the label, when in the label, because I only have to break it on a target address. So I have a much longer list. And there's a lot many parameters in the label. But when I change into this structure, I have to cut the if, else, then. So that has to be cut. And then I have a shorter parameter list. But I forgot to change the length, and then it assembles funny things. So this is the original force, and basically this force can be translated into the macro assembler almost word by word. Okay. Okay. So this force in the compare force in the real force code and force code in the 6.2 and force code in 6.1. And the advantage, of course, is that force resolve all the forward and backward referencing automatically. So if else then conclusion. So macro assembler in C is now extended to be a fourth metacompiler. And intricate fourth words and control structure can be compiled faithfully in C in a single pass. Okay, how's that for C modification laboratory? Okay. Okay, let me just show you this compiler, how this compiler actually works. So here is the C, all the C code, but let's don't bother with all these things. Let me just show you after it compiles, it spells out all the information that it compiles. Oh, okay, let me just do reset. Okay, now it is reading the file in Flash and compiles it. Okay, so this is I think your robot code will be put in that file, and then it would automatically assemble, compiled.
Where's the compile taking place?
The compilation takes
On target.
on target, because it's a C code. This macro assemblers are defined as functions at the beginning, and you have the Arduino has a setup and a loop. So all the macro assembler are assembled, executed in the setup loop. Okay, so it enters into setup, and then it runs the metacompiler. So at the run, it compiles the dictionary, and once the dictionary is finished, it jumps into into eval, and then everything works.
So it's like one line of code in loop.
Hmm?
Well, it's just one line of C code in loop to jump into the starter.
Yeah. Well, let me just show you the compilation. Okay, this is the last time. the same dictionary dump. So here is the reset. So this is the ESP32 reset. Okay, I think that's the code release the code June 8th, 2016, and then reset it dump make a kind of memory dump and boot 6.2, and 6.2 it just when it's compiling all the primitive code, it spell out the name and then the code sequence. I think the name and address and the code sequence. If that's labeled, this is it would. I'm sorry. So here is the dump between the two link fields. So you have the name field and then the code. So here it dumps out all the thing. I was just dumping everything out for my enjoyment, and I should have delete all this print statement. But the print statement just go through everything, and then it's compiling all the colon words. Okay, and at the end.
It's nice to see something happening now.
Well, it's kind of funny that this compiler. We always think that the compiler would compile something, and everything's done, and that executable code would be executed. But this thing, because I'm putting the macro assembler in the setup root, so every time it boots up, it builds a dictionary and then runs it. So I don't know. I think right now it looks just pretty. Here is the dump from memory 0, but at last IP equal to 8688. That's the size of the dictionary at that point. And then I also print R stack equal to 0. That's very important because R stack was used to do the compilation. If the structures are not compiled correctly, this return stack may not be 0. Okay, so that's one thing I have to check.
So so right now it actually builds the system every time you reset.
Yeah, right.
So
right.
in the future,
Mm-hmm.
we could just copy this memory, put it on the disk, and have a little bootloader that just loads that into memory and jumps to it, right?
Mm-hmm. Yeah, right.
This is great for
Okay.
development.
Yeah. It's just that I need to see everything to make sure things are run.
Compile complete?
Hmm?
Is the compile complete now?
Yes.
Does it do something?
Well, you see, it's force is running. Okay. Yeah. So here, I make sure that R is 0. If R is not 0, things are not correct. So at here, so here force is running, and we can words, right? And if I do the 4, yeah, it drives the motor, right? If the motor is attached to this 4 and back, it lifts up 2 other ones, and stop, turns it off everything. There's onboard LED, which I like very much because every time force compiles, I always lit that blue LED up.
Oh, is that it?
If the blue LED is not lit up, force is not initialized correctly. Okay, so this blue light always gave me assurance that something was done right there. Okay.
Super
Yeah.
This is like, you open this door and you walk through this valley, this very, very, very big valley. Would I want to go through that valley of making a fourth with C? Or would I want to go through the bare metal fourth on the hardware?
Mm-hmm.
I mean, this is sort of like, it's like the opposite of this one.
Yeah, right.
Why would I want to do one? If I went through this, would I still have access to all the other stuff that comes with the Arduino?
Right. Exactly. That's a reason to do it.
That's the reason to do it.
Because I just cannot write that Wi-Fi stack. Right. There's no way that I can write it.
Another Arduino that
Yeah.
has Wi-Fi.
Philosophical discussions can wait till during lunch, and if you want to
Mhm.
share them, maybe after lunch.
Okay.
Ting, we know your email address got
Hacked. Right.
I suggest that if people want to contact you
And
going forward,
uh,
maybe go to Google and say to Google, when is the next SVFIG meeting?
yes.
And that'll bring you to the agenda page. It ends in what, .io? Anyway, you should be able to find the agenda page.
Mm-hmm.
Then my address, which says Fourther at something.
Right.
Is on the agenda page. Just send me a note, send me an email saying you want to talk to Ting, and I'll forward it, and he'll either contact you or not.
Right.
And it may be, no, it may be that he will join the email list in his new incarnation. But that may be not a good idea.
That's okay.
Right.
But for everybody here, that
And on the internet, there are enough pixels.
Put your hand over there.
And if you can't read that, send an email to me. You know my email address, and I'll forward it on to Ting.
yeah. So this is my current Gmail address. Okay.
Because George is here, we can't say to George, George, did you subscribe to Ting? Probably the bathroom, if I remember.
That's an
HANSUNDING.
So
Okay.
Ting?
Ding. Okay. And
Is it going to be shared right away, or is it going to evolve a little and then?
yes, it will be shared. I think. Another thing is I closed.
The reason I asked is there was a guy on YouTube in the chat
Mhm.
that asked this very same question.
Yeah, right. I think I have decided to close down the web page I have on Gmail. Yeah, because I'm tired of paying $12 a month and not get anything back. So I've closed down everything, but I intend to give all the Office store to Dave, so you can publish it on the FIG website.
Okay, assuming that.
Yeah, I was looking at the website. Oh, I can't get it. It's done. But I think I'll hand you all the files,
Okay.
and you can.
So this room is not lockable.
Okay.
So somebody could stay behind and we can get something for them, or I hate to have you take a chance.
I can stay. Give me a burger.
Yeah.
What kind?
Straight old burger.
The fries?
Yeah, and a drink.
Do you want cheese on it?
Plenty of drinks. Why don't you do that?
There's drinks in the cooler over there.
Let me use the restroom first.
Okay. I just.
I'm missing a lot of stuff.
Oh.
I don't know how to deal, for the Raspberry Pi has more things to it. For the Arduino environment, I don't know how to deal with it. So,
Oh, it's much simpler.
yeah.
It's much easier. Yeah, I
But
just
have to
couldn't.
see to do sketches, right?
Yes. It's